You're coming in this morning, we're going to open in your notes on the definition of a derivative with number 6 and 7. Right? If you have been at home and just working from the notes and don't have a copy and you'd like a copy, there are some on the front table. Okay. Those are probably especially very helpful for you tomorrow. You really haven't needed them yet, but they will be especially helpful for tomorrow. Okay. All right. We're going to approach your opener first of all graphically, and that's why I've drawn a graph here. So we're finding the derivative of the absolute value of x minus 2 at x equals 3. If you didn't draw a graph, I want you to do this. This is important conceptual understanding. And go over here on x equals 3, and let's put us a point there. We'll label that as the point 3, comma 1. Okay. Now, especially as we're now moving forward, we're going to run into a potential issue in calculus that there's really two things in every problem that's going on. Okay. There are, we'll call it algebra. There are some algebra skills. All right. I'm working all this out to get an answer. And then there's I actually understand what in the world I just did and what that answer means. You're going to have to be honest with yourself right up front. Okay. When I see this word derivative, I'm calculating answers for my homework. I'm getting them right. But do I really know what I'm doing? Conceptually, when I deal with the derivative, I want to link. All that means is, oh yeah, it's just slope. I don't lose sight of that. Every time I calculate a derivative, it's just slope. All right? It's just slope. But slope means I got 2 points. So let's give ourselves another point here on our curve. And don't draw yet, because I'm going to show you where I want you to draw this. Now, right now, if I found the slope between those two lines, those 2 points, what would we be finding? Please don't tell me derivative. That's average rate of change, okay? And for 3 weeks now, we have been trying to stress really, really, really hard. How do you go from average rate of change to instantaneous rate of change, a derivative? What do? We move the points closer and closer and closer and closer together. Now let's draw at this point really close to 3. Okay? And we're going to draw the tangent line that goes through those 2 points. There it is. Graphically, from the picture, can you tell me what that slope is? What is it? It's 1. That slope's 1, and we can see that in our picture. Okay? Now, we're going to do it algebraically because there's a couple important things to understand about the algebra. But we're going to do exactly what we just did in our picture. Okay, we're finding slope. The change in y divided by the change in x. And we just took those 2 points and we moved them really, 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 really close to 3. That is our derivative. The derivative of y with respect to x evaluated when x equals 3. Now, I cannot do this problem without knowing what absolute value of x minus 2 is. I have to have the piecewise definition of this little graph. It is the line x minus 2 when x is greater than or equal to 2. That's the line we have here. Of course, there's part of that that's missing. And there would be the rest of that line. Well, the other line in our absolute that makes up our value, that makes up our v, is just the reflection of that. The opposite of x minus 2. when x is less than 2? Very, very important question. If we're dealing with x approaching 3, do we have x's that are bigger than 2, less than 2, or both? We are greater than 2. Because, yes, Mr. Epling, you could be way over here and you're approaching and getting closer and closer and closer to 3. That's not instantaneous rate of change. Instantaneous rate of change is we're getting very, 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 very close to 3. And no matter what, close to 3 is going to be bigger than 2. So, in our piecewise, we can replace absolute value with what it's equal to. It's equal to x minus 2. So the limit as x approaches 3. And we do have x minus 3 divided by x minus 3. And so algebraically, we get exactly what we saw graphically. And our pictures should tell us the same thing that our algebra does. And so we get a slope of 1. But number 7 might be even more important. Number 7, take the derivative of y with respect to x and evaluate it when x is equal to 2. Oh, so now we're talking about we want the slope right here at the point 2, 0. Now let's start just like what we did before. Let's deal with it graphically first. So let's give ourselves a point really, 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 really close to 2. So here we are. Tell me about the slope of that line. It's positive 1. But wait a minute. Mr. Epling, what if you were really, really, really close to 2 on the other side? Oh, it's negative 1. Okay, so which one do I choose? Do I choose positive 1 or do I choose negative 1? Positive. How come? Okay, it's absolute value, right? I mean, everything is positive. It's not positive 1. So what should I choose? It's not negative 1 either. So let's look at the algebra to see why. Okay, so change in y, the absolute value of x minus 2, divided by the change in x. We're wanting the slope here at 0. And we're moving points really, 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 really close to 2, not 0. Okay, now, ignore for just a moment that we're doing anything with the derivative. We are evaluating a limit. Anytime you evaluate a limit, what do you have to think about? Oh, I got to think about both sides. I have to think about in this problem, what's the limit as x approaches 2 from the left? I'm not going to write minus 0. And I also have to think about, what's the limit as x approaches 2 from the right? I'm looking at the slopes of my secant lines as I'm getting really close to 2 from the left, and I'm getting really, really close to 2 from the right. That's what we drew in our picture. And what I'm wondering is, hey, are these the same? Well, if you're approaching 2 from the left, do you have x's bigger than 2 or less than 2? Those are less than 2. So we can replace that absolute value with the opposite of x minus 2. And we get exactly what we saw in our picture. That slope is negative 1. But if we're approaching 2 from the right-hand side, we have values that are bigger than 2. And so we're going to replace absolute value with what it's equal to, which is x minus 2. And what we see is exactly what we saw graphically. We get a slope of 1. Those two things are most definitely not equal. So what's the slope of my tangent line? I don't have one. I don't even have a tangent line I can draw because I don't know what slope to give it. This limit does not exist. Whether I look at that algebraically and I see the limit from the left and the limit from the right aren't the same, or I think about those limits graphically as I move those points really close together from the left and from the right, those slopes aren't the same. I do not have a derivative at x equals 2. So let's write on our picture new vocabulary that we talked about yesterday. This particular function, the absolute value of x minus 2, is not differentiable. That was new vocabulary from yesterday. At x equals 2. It does not have a derivative. It doesn't have a slope of a tangent line. It doesn't even have a tangent line at x equals 2. Okay, now important to see if our vocabulary sunk in yesterday. The absolute value of x minus 2. Is the absolute value of x minus 2 a differentiable function? Is it a differentiable function? Why, Noah? Okay, this is not a differentiable function. It is not a differentiable function because there is a location, x equals 2, where I can't find a slope, and I'm going to have to abbreviate differentiable there. But that location, x equals 2, is in the domain of y equals the absolute value of x minus 2. This is not a differentiable function. Yes, ma'am. I always check on both sides. It's a limit. So I'm always, always, always checking on both sides. I did a number 6. You remember when we drew our picture and I drew the point on both sides? No matter which side of 3 I'm on, I'm bigger than 2. And so this is both sides. I didn't write left and right, but I did think about it, right, as I come through there. All right, now, this problem we start with as our opener, the absolute value of x minus 2. Rashida, is it a continuous function? Yes, this is a continuous function. It's continuous everywhere, which happens to be its domain. Well, let's label that. That's kind of important because that means I can have a function that's a continuous function, but it's not a differentiable function. And we haven't seen very many of those. In fact, I only think we've seen one example in all the times we've been dealing so far with slopes, with derivatives. Absolute value is a good example to illustrate that. It's a continuous function. It is not a differentiable function. There is a location on its domain where I can't calculate a derivative. Now, are there any questions at all there with your opener? You're working on your homework the last few days. I hope you've been going and looking at the solutions Mr. Epling is providing, because I've been trying to give you different notations. Sometimes using Newton's notations for derivatives, f prime, and sometimes using Leibniz notations for derivatives, dy dx. Take the derivative of y with respect to x. We need to understand both notations and the reason for the two of them. The prime notation allows us to look at derivatives as functions, just functions with a different name, the name f prime or g prime. Leibniz notation reminds us this is slope, the change in y divided by the change in x. And I don't want you to lose sight of the fact that when we deal with Leibniz notation, The d divided by dx, it's an operator. It's not adding, it's not subtracting, it's not multiplying, but it is an operator. And sometimes students will look at this and they'll say, well, d, dx, f, that looks like multiplication. It is sort of multiplication notationally, okay? Just like if we multiply fractions, 1 over 5x is 2 over 5x when we multiply it by 2. That's the idea notationally what's happening here. There is no multiplication going on when I do a derivative. But notationally, that's what's happening. df dx is the same thing as take the derivative with respect to x of a function named f. But this is an operator, and that's going to be very important later on in our course. Now, also understand at this point, the whole respect to x thing probably doesn't make much sense at all because it's all you've done. But eventually, we're going to take a problem like 1 over 5x, and we're going to take the derivative with respect to t or respect to y. Okay? We're just not there quite yet. Emily? The definition, this would be read as f prime, y prime. Okay? And that's what we have here. This is really not a definition. It's just how we read that. Up to this point, that's primarily what we've dealt with. What we call first order derivatives. But we have seen an example where we could deal with derivatives of other things. So if we use, for example, the problem number 7 you all just asked about in your homework, we had the function y equals x squared. We took the derivative. We got 2x. Does the function y equals 2x have slopes? It does. We call those higher order derivatives. A second derivative, for example, f double prime of x, y double prime. We've only seen that once. We're going to see it a lot. We haven't seen a reason why would I do this. And if we wanted a derivative 3 times, we do f triple prime of x. Once we get bigger than 3, we start using Roman numerals. Right? A 4th derivative. V would be a 5th derivative. Vi would be a 6th derivative. In a Leibniz notation, take the derivative twice of y with respect to x twice. Now, that looks like exponents. It's not. Okay? We're not squaring anything or cubing anything or raising anything to the 4th power. Okay? It's just simply notationally how we notate. We're going to take a derivative multiple times. Okay? I am trying in the solutions that I provide for you to mix between the two because you've got to get comfortable with both of them. They both have advantages. Okay? Tomorrow, primarily, we are going to deal with derivatives graphically, and function notation will be very, 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 very helpful. As you deal with derivatives algebraically, I'm going to be honest, I prefer Leibniz notation. It reminds me, this is slope, the change in y divided by the change in x. And that's exactly why it's written this way. It's d as opposed to delta because it's an instantaneous change, not an average change, okay? Not over an interval. Are there any questions at all with our notations? All right. Then I would like you to try problem number 8. For those of you that are at home, when you're done with problem number 8, you're going to, over on the chat side of things, send me the answer. You're just going to type it. Number 8 is mostly an algebraic skill type of thing. Because I'm not asking you to interpret. I'm just asking you to find, differentiate, find the derivative. Okay? But I want to make sure we have that part sorted out as we go through. All right, so problem number 8, we're differentiating. Okay? And a couple of you, I love what you did, that you started and you drew yourself a little picture. It's a really, really good idea. Because what we're wanting to know with this graph is any of these slopes of these little red tangent lines that I've drawn on the graph. Not a particular one, any one of them. And so we're looking for the change in y divided by the change in x. F of x plus h minus f of x divided by x plus h minus h. And we're looking for those 2 points to get really close together. And as we do, h is going to approach 0. Now, let me tell you the most common mistake that students will make in this problem. We won't name any names, that we had somebody do that. I'm going to evaluate this limit, and I'm going to multiply by a well-chosen one. The most common mistake is to get in a hurry, and I'm going to undo the correctness and multiply the numerator, but forget to multiply the denominator. That is the number one most common mistake when I deal with a rational function, is to forget to actually do the multiplication I wrote down I was going to do. Now, there is a lot of algebra involved here, and keeping up with all my details. That is why your homework is so important, to practice that algebra piece. Conceptually, line 1 is it. I know it's slope, and I'm moving 2 points together. But algebraically, there's a lot going on there. I got to multiply. I got to make sure I fully distribute this subtraction, that I don't make careless errors in doing that, collect like terms, and then evaluate a very simple limit, so that our derivative is negative 3 divided by x minus 1 quantity squared. Now, I would not do this with the alternate definition of my derivative, f of x minus f of a divided by x minus a. It will work. Just make sure when you get to the end, you don't write your answer in terms of a's. There are no a's in this problem. Negative 3 divided by a minus 1 quantity squared is not correct. It is not f prime of x. Now, you can fix that fairly easily, but I would use my standard definition when I'm looking for the slope anywhere. It tends to be a little bit easier. Okay? Now, today, we're trying to tidy up and clean up algebra stuff. Tomorrow, we're going to talk about finding this derivative only graphically, looking at those little tangent lines we've drawn and drawing out their slopes. What does the graph of the derivative, without calculating its equation, what does it look like? Right? That's what we're going to look at tomorrow. Tonight, you have a little practice with a little bit more work with our derivatives. Now, the practice that you have tonight, I've broken down into sort of 2 parts, the first 7 and then the last ones. The first ones, you're going to work on your algebra. The second ones, I'm just asking you to identify, okay, I'm telling you this is a derivative. What are you taking the derivative of, and where are you taking the derivative? I cannot stress to you enough how important the last half of that is, okay, for a few days from now. I also, yesterday you had a little video on evaluating derivatives from a table. At some point during the day, that disappeared out of Canvas. I don't really know why. So I posted it back, but I gave you through Sunday, since yesterday was a virtual day, which was why you had the 10-minute video. So I did post that back in Canvas for you on today's assignment, so you should be able to see that. If you've already done it, you don't need to do it again.